Good evening. I'm Yvonne Stapp for Science for the Public, and I welcome you to tonight's Contemporary Science Issues and Innovations program. Our topic is time travel, and our guest is David Toomey, Professor of English at UMASS-Amherst, co-director also of the English Department's Professional Writing and Technical Communication program. Dr. Toomey's teaching and work reflect a very broad background and expertise, which includes several areas of literature plus science and technical writing. This scope may help to explain his particular gift for translating exciting but difficult concepts in physics, cosmology, and astrobiology. He's the acclaimed author of a number of popular science books. Tonight's discussion, based on his 2007 book, The New Time Travelers, A Journey to the Frontiers of Physics, was among 10 nonfiction books named New and Notable by Scientific American in 2007 and listed among the best sci-tech books 2007 by Library Journal. His 2013 book, Weird Life, The Search for Life That's Very Different from Our Own, was longlisted for the 2014 Penn and E.O. Wilson Literary Science Writing Award and shortlisted for Physics World Book of the Year for 2013 and named an editor's choice by the New York Times Sunday Book Review. Tonight, Dr. Toomey will explain why time travel is so alluring, not just for science fiction, and he'll tell us about the major contributions to the development of the idea. He'll also talk about the significance of science fiction in the evolution of the idea of time travel. It's our great pleasure to welcome, by Google Hangouts from Amherst, Massachusetts, David Toomey. Dr. Toomey, welcome.
Thank you, Yvonne.
And I'll start off, since we're going to talk about time travel. There is a lot of confusion around the concept of time, a lot of dispute. What is it about time that is such a problem?
Time is a problem. Short answer is because no one knows what it is. St. Augustine, many centuries ago, I'll paraphrase poorly, but he said something like, I know what it is until you ask me to explain it. And in fact, it's still pretty difficult to explain. In fact, physicists today do not have a good definition of the word now.
Right, I get that idea that they don't seem to have it, because one of the difficulties that is in physics, it seems, from here, that it is isolated from a material context. So it's hard to think of time without change, and change has to happen in a material context, and a material environment has to be something. So that is perhaps one of the difficulties, that in physics it's sometimes just treated as a maybe separate entity. But in any case, could you give us a little background about the concepts that from physics that are most significant to the idea of time travel?
Sure. The most significant concepts are Einstein's special relativity and general relativity. Special relativity presents a concept of time as part of space. The idea that time and space are inseparable, and a physicist would call them space-time.
Right.
You have to, this seems counterintuitive to us. We think of space as having 3 dimensions: height, breadth, and width. And in fact, there should be properly seen, the universe we know has 4 dimensions, the 4th dimension being time. The idea seems counterintuitive to many people. It's not counterintuitive if you think about it a certain way. One thing I might say, and I'm not the first to say this, is that it's quite impossible to imagine a point in space that's not also a point in time. For instance, imagine, if you can, the room you woke up in this morning. If you imagine that, try to imagine it now, you'll imagine it maybe at 9 a.m. or 7 a.m. or 6 a.m. But try now to imagine it at no particular time. I think you'll find you really can't. Alternately, try to imagine a point in time that's not a point in space. Say, for instance, a minute before midnight on New Year's Eve last year. You might be able to imagine it at Times Square or wherever you happen to be at the time, but I think you really won't be able to imagine it without also imagining a point in space at the same time. You, as it were, one might conceive of if I ask you to imagine a point in time but not a point in space, you might come up with a digital clock, a readout of 11:59, or an analog clock or a calendar. But those are just symbols and rather awkward ones. I think you really can't do it. So this is a long way around the barn to say space and time are inseparable.
But then it's just difficult to imagine now traveling backwards, say, in time. Can you help us out with that? How can you travel back in time? I know that the theory said it should be possible, theoretically. What does it mean to travel back in time?
To travel backward in time, to understand how one might travel backward in time, one first has to understand how one travels forward in time. Now, traveling forward in time, let's call it futureward time travel.
Yeah.
This is a prediction of Einstein's special relativity, the theory of relativity Einstein put forth in 1905. So, to travel forward in time, of course, we are all traveling forward in time 1 second every second, 1 hour every hour, 1 day every day. That is futureward time travel in, we might say, the trivial sense of futureward time travel. But Einstein's theory of special relativity declared that the speed of light is fixed. The speed of light is constant. It cannot be changed. It's 186,000 miles a second or 300,000 kilometers a second. So very, very fast. But it is fixed. Meaning, if I am standing still viewing a photon traveling at the speed of light, I'm going to measure the speed at 186,000 miles a second. If I am going at half that speed alongside it, I am still going to measure it at 186,000 miles a second. Now, this seems quite counterintuitive. And the only way to explain this, the only way Einstein could explain this was a tremendously radical way. He said that distance itself is elastic. So the theory of special relativity predicted, among other things, that distance could shrink and expand. The special relativity means makes a few predictions that are pretty bizarre and counterintuitive, but they are counterintuitive only because we don't travel at relativistic speeds, most of the time anyway. One calls upon what many people know as the parable of the twins to explain how futureward time travel might work. So suppose you have twins, and suppose you have twins. Here's twin number one, okay? Here's twin number two. Twin number one stays on Earth. Twin number two travels very far away from Earth and back again at relativistic speed. That is the speed approaching the speed of light. Suppose this travel, this journey into outer space and back starts today in 2018. And suppose it takes 10 years as measured by twin number 1, who stays home. The closer twin 2 travels to the speed of light, the slower his clock will tick. And if he wanted to travel very, very close to the speed of light, it would tick, in a 10 years time measured on Earth, it would tick only an hour or half an hour or a minute. So when he returns, you see, he will have effectively traveled 10 years into the future. So he returns at 2028. He's only an hour older, or half an hour older, or a minute older, depending on how close he travels to light. His twin, the stay-at-home twin, is really 10 years older. So twin number 2 effectively has traveled into the future by 10 years. And there's nothing about that that's science fiction. That would happen, and it does happen. We have measured the effect, physicists have measured the effect innumerable times. Of course, we can't travel near the speed of light right now, but we can use very, very sensitive clocks like atomic clocks.
Right.
One experiment, you keep one clock at home, and they are synchronized. You take the other clock and you put it in a jet aircraft and you fly it around the world once or twice. And when the second clock returns home, you will find its clock had ticked at a lower rate, at a slower rate than the other one. So it had effectively traveled into the future. Fraction, but that is time travel into the future.
Right. This part is understood that in principle this can happen, but in fact we don't know of anything material that can travel at the speed of light. That's a small problem, but let's just say for the moment that we're going to travel forward or back. There are these mechanisms or machines, the time machines and so forth, that are supposed to take us there. Can you tell us about that?
We should make clear that there's no theory of time travel that talks about traveling at the speed of light. Only light travels at the speed of light. The future word time travel scenarios I just described, one travels near the speed of light, but not at the speed of light.
Right, and okay, yes, fine, okay. Then, so however we get there. Now, I just want to just introduce this to remind everybody that there have been many examples in science fiction, certainly, but also the great scenes out of the Christmas Carol where a person can travel back and observe past events. And but the person is observing the past events, and in almost like the way we do with dreams or something, you cannot interact, you don't really reconstitute the event. Is that true? And in time travel, in traveling back, and I'm thinking of the grandfather paradox and so forth, the idea is that you somehow interact with a past event. Which is true, and how do we get there?
Okay, we can. It's not difficult to visualize the past. We're always doing that.
Right.
That is because the speed of light, although very, very fast, is finite. So when you look at the moon, you are seeing the moon as it was 1 1/4 seconds ago.
Right. Okay.
When you look at the sun, you're seeing the sun as it was 8 minutes ago.
Right.
So if you went very far from Earth, say 100 light years from Earth, and you had a sufficiently powerful telescope and pointed at Earth, you would see things on Earth that as they were 100 years ago.
Right.
Now we wouldn't, physicists would call that time travel.
Right.
But that is seeing the past. We're always seeing the past. How do you, how do physicists talk about doing it now? Pastward time travel requires, or it is made possible, I should say, by Einstein's ideas of general relativity. General relativity is an enlargement of special relativity. includes gravity. Special relativity did not account for gravity, had no way of accounting for gravity. But general relativity, roughly speaking, says gravity bends space-time. So to make one way to make a time machine would be take a wormhole. Mm-hmm. A wormhole, as our viewers may know from countless science fiction stories, is a tunnel through space-time. And if you a wormhole, here's a rough diagram. Suppose we have a wormhole here. This is one mouth of the wormhole. This is the other mouth of the wormhole. If I connect these, I fold space-time, as it were. Okay, yeah. So I can come in. I can just punch through space-time, and I come out here. Right, I can walk through the Earth mouth of the wormhole, and come out the Arcturian mouth of the wormhole. Right. So I have not bothered traveling those 36 light years. But now, suppose I treat the mouths of the wormhole the way I treated the twins. I take one mouth and I move it at near the speed of light away from the other mouth and back again, so they're side by side again. At this point, the stay-at-home wormhole will be 10 years older. It'll mm-hmm. be in 2028. The moved wormhole will not have aged as much. Say it aged only an hour, the way the traveled twin aged. That would mean I could jump in to the mouth of the stay-at-home wormhole in 2028 and emerge from the mouth of the moved wormhole in this year, in 2018. So that would be a kind of time machine. That is the most common idea for a time machine.
Okay. Now, do you physically enter the wormhole, and are there any conditions on us physically if you do this kind of strange trip?
Well, yeah, there are. There's it's strange to say, there are physicists who have written papers explaining how it might be done. It would only be done with great amounts of energy. You can't, if we could make a wormhole, keep it open long enough for someone to go through it. Some calculations have suggested it would take the energy of 3/4 of the stars in the Milky Way galaxy over a year, the energy output of 3/4 of stars in the Milky Way.
And then you hope it stays open?
Yeah. So there's one difficulty there, just making the thing. Yeah. There would be, there'd probably be some kind of physical challenges to the human body as well. Gravitational stresses might be enormous. Human body might not withstand it. There are physicists who work around this, and yeah. They talk about benign wormholes in which the stresses wouldn't be so great, or ways to shield the radiation. Radiation effects might be pretty severe too. But to some theoretical physicists, thinking about these things are just fun. And they're not insurmountable problems for a civilization which can harness the output of the energy of 3/4 of the stars in the Milky Way.
Right. The idea then definitely assumes physical movement through space-time, right? Mm-hmm. Of physical bodies moving backward or forward in space-time. By various, there are different kinds of constructions, wormholes, and I think there's another one of this particular cylinder in space, and there are all sorts of things to get you there. But the idea is that you physically move human beings from this point, the present, either backward or forward in time, correct? Mm-hmm. Okay, all right. But just to get that straight. Then the other is you interviewed a number of really interesting physicists. People might really enjoy reading about them. It's very interesting, the different kinds of ideas that came up. Would you mention like 2 or 3 people that you consider major contributors to this idea?
I think Caltech physicist Kip Thorne,
Absolutely.
who recently is a recipient, one of the co-recipients of the Nobel Prize for the
Yeah.
discovery of gravity waves. Thorne may have done more to introduce the idea or make the idea of the study of time travel, password time travel, of some interest and perhaps respectable by physicists. He was called on as a consultant for the film Contact, which
Yes.
was produced by Carl Sagan. It's, I'm forgetting the year, 1990 something. But Sagan wanted a realistic wormhole in the film, and Thorne advised him on it. The film wasn't about time travel, but Thorne went away from that, thinking harder and harder about it all, and sometime later came up with a paper, one of the first papers that discussed how one might do it realistically.
Yeah, that's interesting because Kip Thorne has been so important in the idea, as you mentioned, of the gravitational waves. And for a long time, there were people that had doubts about that too. And then I guess general relativity did predict such things, but there was no way to prove it. And then very recently, it was just a tremendous accomplishment. So maybe this will come true in time as well. But he has a tremendous imagination in addition to the brilliance. There are other things, and you address this in the book. There was a need for new mathematics or advances in mathematics in order to build this kind of theory. Is that true?
Most the types of time travel I've discussed are pretty logical consequences of special relativity and general relativity. But to create those theories, Einstein needed a new kind of geometry, not the Euclidean geometry that most of us learned in high school, geometry on a flat surface. Einstein needed geometry that would work on curved surfaces, a different kind of mathematics, and it is called Riemannian geometry.
Okay, so there's just a very advanced, several very advanced ideas along those lines, but that's not so familiar, I think, in general. And it's interesting how much these new geometries have contributed to not just this concept, but a number of other concepts. I'd like to turn now to your writing, your own background, which is kind of unusual. You started out in literature, is that correct?
Mm-hmm.
And why did I think you were a Faulkner specialist? Is that true, or did I make that up?
I studied Faulkner in graduate school.
Okay, so there you were reading William Faulkner, and you got interested in science. Were you always interested in science? Do you have a background in that also?
I was interested in science when I first learned what science was.
Now, what do you mean by that? What, does it mean early on, or?
Yeah, I suppose. I can't remember not being interested in science. I mean, in what we call, like how high clouds are, how far away the moon is.
Yeah, yeah.
As a child.
It's interesting just because sometimes there's such antagonism in the liberal arts, toward the sciences. And in fact, there are many areas to be friendly about, that there should be much more mutual interest. I wonder if you think that your literature background contribute to your writing abilities for these very difficult concepts like time travel.
That might not be for me to say. I don't know.
Okay, you don't feel that the literary background necessarily influenced it.
I would expect that reading good writing
Yeah.
helps you be a better writer.
Well, what I mean is that some of these concepts are extremely abstract. It's really quite difficult. You have to spend a lot of time getting really acquainted with the concepts. And I'll point out that I'm not thinking just of this book, but your other one, Weird Life, where the examination of this, the biochemistry, it's a very difficult task, and you took that one on also. Do you have any projects going on now in science?
I am thinking about projects involving animal behavior.
Okay. All right. And is that underway, or is that just a prospect?
It's just a prospect.
Okay. All right. Well, we'll wait for that one then. In any case, I want to thank you very much for joining us by distance tonight. And I wish you very, very well in the future. And thank you for writing these wonderful books for us.
Thank you.
Good night.